I'd like to talk about how to graph this function. In class, we've talked about how we graph y equals log base 3 of x by taking the inverse of this. So the inverse would be 3 to the y equals x, and then we replace the x and y's, and we get 3 to the x equals y. Okay? But how do we address this situation when we have a multiplier out in front, we're subtracting from the x, and we're adding to the entire thing? And it's all about our transformations. The first thing that you're going to want to do is recognize what your kind of parent logarithm is. So our parent logarithm is log base 3 of x. Okay? Now, we know that that turns into 3 to the y equals x, which eventually, as a change the x and the y's, we get 3 to the x equals y. So we should have the ability to graph that. Now I know off of just the standard exponential function, we should have the points 0, comma, k times 1. We should have 1, comma, k times a, and should we have negative 1, comma, k over a, where k is our multiple up front. Okay? So in this case, it's just a 1. So I'm just going to actually just write these as 0, 1, a1, negative 1 over a. Okay? So I should have those points. So on 3 to the x equals y, we should have those points. And if I'm doing this process, I'll never have a k out here other than 1 for this, because when a k is a different value, that's going to be taken care of instead of by what we're doing here with the k, but by the vertical stretch when we actually use our transformation. So if these are on 3 to the x, then on log base 3 of x should be 1, comma 0, a, comma 1, 1 over a, comma negative 1. Okay? And now because obviously we know our a is 3, this would have been a 3 there, this would have been a 3 there, so it's 1, comma 3, negative 1, comma 1/3, and same over here. So a was 3, so I have 3, comma 1, and 1/3, comma negative 1. So those are points that are on that parent function log base 3 of x. And if I just graph log base 3 of x real quick for you, put in 1, comma 0, put in 3, comma 1, and put in 1/3, comma negative 1, you see that those 3 points are indeed there. So if those are the 3 points on this parent function, let's look at the transformations that are applied. Remember, we have this phrase HSRV, which means horizontal movements, stretches, then apply reflection, and then to apply a vertical. Okay. Remember, horizontal, the only thing that's impacted are your x's. When we do stretches, it's x or y, so pay attention to what component is doing the stretch for you. The reflection, again, is the x or y. The vertical is just applying to the y. Okay. So I'm going to try to figure out how I change these 3 points based off of that number, and that one. Okay. So when we do, so talking about the horizontal movement, here's a horizontal movement. So that's going to change, and remember it's -1, so it's actually moving to the right. So it's going to take this point and move it to the right 1 unit. So take that point, move it to the right 1 unit. So take that point, move it to the right 1 unit. So it becomes, what, 4/3, comma negative 1. Okay, so I've taken care of that negative 1. So I've done the horizontal movement. Now we do a stretch. So it's a stretch here of 2. It's a vertical stretch of 2. It's out in front, so it's a vertical stretch of 2. So all these y values are going to change by a multiple of 2. So that one can stay 0. This one becomes 2, and this one becomes negative 2. Now that negative out front is going to change the y values to a negative value. or the opposite. So here it's a 0, make it opposite 0. 2, make it opposite, becomes -2. -2, make it opposite, becomes +2. Okay, so taking care of that. We did the horizontal, we just did the stretch and reflection, and now we'll do the vertical shift, and that is adding 4 to everything. So this number becomes 4, this one becomes 2, and when I add 4 to this one, it becomes 6. So these 3 points should be on that curve. So let's go ahead and plot those 3 points. We have 2, 4. We have 4, 2, and then we have 4/3, 6. And they're starting to look like they're belonging on one of these logarithmic curves. If I graph that thing, you do see if those 3 points end up being on that graph. So it's kind of the way that I think is the most efficient way of developing a logarithmic function that has been transformed. Okay, move left, right, up, down, stretch, reflected, that kind of thing. Let me know if you, I don't think you get that involved in your homework. Okay, you're not going to get that involved on a test question, but I think that is good to look at and have that insight of the fact that the transformations are the exact same as what we've talked about through all other functions.